Okay, so welcome this afternoon for the WED3 session. This is about computer vision and recognition. I am Philippe Martinet from France, École Centrale of Nantes. I have the great pleasure to welcome Jana Koseka from John Mason University. She will give a keynote on semantic parsing in indoors and outdoors environments. So please, Jana.
Thank you. So good afternoon, everybody. So I'm going to talk today about some of our experiences for semantic understanding of indoors and outdoors environments, and how to do this in the context of different robotics applications using multiple sensing modalities, and how to be able to process efficiently video streams. So let's first have a look at what do we mean by semantic parsing. When I refer to semantic parsing, I'm referring to the problem of simultaneously segmenting and categorizing partitions of sensory data. And in this case, we are going to consider a setting which would be into the object and some background categories. So here is an example of an image, and the color-coded image corresponds to the pixels being labeled by different semantic labels. So we can label pixels being road, card, wheels, windows, and so forth. So I think there's no doubt that endowing models with some semantic information can enable us to both develop more robust systems and also be able to accomplish more sophisticated tasks. Now, this problem has been considered extensively in computer vision community, and there the approach is typically focused on the single view setting, use various machine learning techniques and pre-processing techniques, which are often computationally expensive. And a lot of the challenges in that community have to deal with scaling the techniques to a large number of semantic categories. On the other hand, in robotics setting, we really have requirements that we would like to be able to process multiple sensing modalities, which we often have available. We would like to develop techniques which are efficient and can seamlessly process video data. And we also have both an opportunity and also a challenge to develop techniques which can be adopted based on the task. And so we have sort of set forward to revisit this problem with these constraints and sort of see. I'm going to talk a little bit about some of our findings. So if we think of various robotic tasks, for example, the task of navigation and the type of semantic information you may need in order to accomplish this task, it is often sufficient for you to know where road is or where the free space is in order to navigate without avoiding obstacles. On the other hand, if one needs to localize, it is important or useful to be able to detect some signatures or features from the portions of the environment which are largely static and do not change so much as a function of, say, season, weather, and so forth. And so here are some examples of buildings and trees, and clearly having some signatures detected on buildings would give us better capability of relocalizing, while trees may be changing a lot with different seasons. And then the last, but not the least, is then that category of objects where we can associate different semantic properties with generic object categories, and then if we need to seek a particular object, then we can refine our representations based on the objects which we are searching for. So when it comes to semantic segmentation, we would like to propose a semantic hierarchy which could be effectively utilized by robotic systems, where we would first like to effectively and efficiently segment and label the video streams into the background and object categories, where the object category would be just a generic category, and these would be regions which are somehow separated from the background by some occluding boundaries. And then if the task requires, we can then refine the object category depending on whether we are engaged in a manipulation task or pedestrian detection. So this can be then refined using some additional computation. So in our setting, these categories will vary depending whether we are in indoors or outdoors environments, but some examples of the background categories for outdoor setting would be, for example, ground, building, vegetation, sky, and object. And notice that here I just have a generic object label, which is anything which is none of the, it's not any of the first four categories. And in indoor settings, we may have ground, furniture, structure, and props or objects. So properties or choices of the semantic categories are motivated by the fact that for the background categories, we typically have a lot of data available, because when we have our robots operating in certain environments, we have a lot of examples of how these different categories look like in appearance, so we can often come up with a very robust techniques which will enable us to classify these based on the available sensory data. And for many of the tasks, these are often sufficient, and then the object category can be refined if we have already a particular object in mind. So I'm going to focus in the first half of my talk about how to efficiently detect these 5 categories, and then in the later half, I'm going to discuss how to then refine the object category into more sort of detailed semantic labels. So another aspect which I would like to keep in mind that since we are dealing with these problems in a robotic setting, different semantic labels need to be often computed at different time scales, because if I need to know where the road is, this is something which I may need to know at sort of finer time scale, because I have to inform my sort of navigation or obstacle avoidance or motion planning module, while if I'm sort of proceeding to do an object search, there may not be such a sort of time pressure to accomplish that. So we would like to define these representations or algorithms which can be adopted and refined, and then consequently will take sort of more time if more detailed information need to be acquired. So as many previous approaches, we are going to formulate our problem in the conditional random field framework, which takes as an input either an image or an image and 3D scan, if available, and output, as an output, it provides the labeling where it tries to assign the most likely label to each pixel or partition given the measurements. So when it comes to conditional random field techniques, there are a lot of choices which one can make. And the choices are related to the fact what are the elementary regions which we are trying to classify, and it can be anywhere between pixels, sort of larger regions which are obtained with some bottom-up segmentation techniques and so forth. So in our case, we are going to select an over-segmentation of an image using the so-called slick superpixels, which are regions of roughly regular size which preserve the uncertainty boundaries. So in a majority of my talk, I'm going to assume that we have also 3D information available, which is registered with the image data. And that 3D information can be either obtained by a depth sensor, either RGBD camera, laser range scanner, or it can be even computed using the structure from motion technique, so stereo or reconstruction algorithms. So imagine now, and this information does not have to be perfect in a sense that I may have regions where I have this information completely missing, and I may have regions where this information is very dense, and we will have our algorithms are going to be sort of handling these situations gracefully. So given this basic representation and the fact that we have 3D information available with each region, typical choices of the graph structure, which induce then the conditional random field, are the ones which consider the neighborhood relationships between the superpixels to induce the graph structure of the final probability distribution. So in our case, what we are going to do is we are going to approximate this graph by a tree by using a minimum weight spanning tree algorithm on the means of the 3D means computed over each superpixel. So as a result, what we will get is we'll get a tree structure where things which are far apart in 3D, the edges will be removed, and the things which are tightly connected and that are close in 3D space will remain connected. And this approximation is meaningful in the context of our problem, where we would like to separate different objects or background from object categories, because often, even though in the image the regions are neighboring, if they are separated in 3D, they likely correspond to different object categories. So this choice also enables us to very efficiently and effectively learn the parameters of the conditional random field and also be able to run the efficient inference. So I'm not going to go to the technical details, but in the conditional random field framework, we are interested in computing the maximum a posteriori estimate of the labels X given the measurements, and then the probability distribution can be factorized into unary terms, which gather the evidences about the presence of different semantic categories associated with the nodes, which are the superpixels in our case, and the pairwise terms are capturing the relationship between the neighboring superpixels, which are close by in 3D. So just sort of one slide on how these are computed. So in our experiment, we have spent sort of quite some time of trying to come up with informative features and effective classifiers. So we just used the nearest neighbor classifier in order to compute the log likelihood of each label per each superpixel. And for the pairwise term, we use just the standard smoothness term. And the feature vector which we are using mostly captures the geometry of the environment. So we compute various geometric statistics over these regions. And the one which is most informative of the object presence are the statistics of the depth differences between the region and its neighbors. So again, without going to the details about all the features, so we can come up with very compact representations of these regions, where in indoors we'll use only 15-dimensional features, and in outdoors we'll use only 6-dimensional features in order to be able to make these predictions what the semantic categories are. And once this problem is set up, we can then effectively learn the weights and also do the inference. And so using this very simple approach and very efficient features, we can achieve the state-of-the-art performance in these 5 categories. And these are sort of some of the competing techniques which both use expensive pre-processing pipelines and also more sophisticated inference. And another reason why we are efficient is because this minimum weight spanning tree approximation is a meaningful one. And this works well both in indoors and outdoor setting. And so if you look at the regions which are labeled red, those are the regions where you can think of them are generating the probabilities where the objects are. And so then we can take these and sample them to actually generate some object hypotheses which are at the level of the bounding boxes, which are the ones which one typically attains using the commonly used object detectors. And then the results are also favorable in the outdoor setting. And so the thing which is appealing, that this choice of the semantic categories, simple features and efficient inference, enable us to run this semantic segmentation at almost 5 frames per second without really needing any special hardware. So another appeal of the conditional random field framework, it's its flexibility. And we will exploit that flexibility in order to deal with the issues of often the different sensing modalities having non-overlapping field of use. So in the case of laser range scanners, we would like to be able to compute the semantic labeling for the entire union of the field of use of the 2 sensors instead of computing it over intersections. And similarly, in the context of RGBD sensing, where the sensor often has a lot of holes due to the reflectance properties of objects and specularities, instead of using the expensive in-painting techniques, which one often cannot afford to use in a robotic setting, we simply use at each superpixel the modality which is available, and instead of having a single graph, we will have our final graph is going to have 3 portions. There is going to be the graph which is going to be in use only by range measurements if available, which is the blue one. Then we are going to have a graph which will be induced by image measurements, if those are the regions where only image measurements are available. And then we'll have an intersection of these 2 graphs where both measurements are going to be available, and we can, in a very flexible way, define these potentials which are depending on the sensing modality, and then learn the parameters of the conditional random field in this setting. All right, so this was the single view setting and how we can deal with multiple sensing modalities. So let's have a look what we are going to do if we have to deal with videos. So given the fact that our graph structure is set up in 3D, we are going to use a lot of sort of exciting work which has been done over the past decades in SLAM, where we can fairly reliably compute the pose between the consecutive views using some simpler feature tracking techniques. So given the visual odometry pipeline, the pose between the views can be computed, and now imagine the following scenario. So I have a graph in view 1, and I can run my inference and compute the probabilities of labels given the measurements in the first time frame. And then my next image comes, but the odometry can inform me what is the relative displacement between the 2 views. And given the fact that the graphs are set up in 3D, I can actually register them in the common coordinate frame. And instead of trying to match the graphs, I will then compute the minimum weight spanning tree of these registered point clouds. And so, as a consequence, the labels computed in the previous frame are then treated as an evidence. And one of the extreme cases would be that the graph will be basically just this forest of trees, so things will be sort of more disconnected. And we have shown that this, again, this recursive type of update and the sort of soft data association mechanism, with these 2 strategies, we are not going to sacrifice much of the performance, and we are going to gain in speed. Okay, so the last part which I would like to discuss is, well, what if we would like to know a little bit more about some of the object categories? Because right now we had a single semantic category which was called object, and this may not be enough for some of the tasks. So clearly, the features which we had were not sufficiently informative in order for us to disambiguate between different semantic categories. So we'll need to develop a richer representation, but we would like to maintain everything which we have already computed, but just compute some additional discriminative features. So for this finer-grained categorization, we are going to tackle it by learning in the conditional random field frameworks per object category grouping rules, which are going to tell us how different superpixels go together in order to generate hypotheses about some foreground-background segmentation. And so, endowing the superpixels with additional features then enables us to basically combine these multiple binary segmentations and generate predictions about large number of categories. And again, using this simple technique while reusing all the representations which we have developed for these other categories, but just refining them and learning more discriminative features, we can achieve the state-of-the-art performance on almost 40 categories for indoor settings. So here, the refinement of the object categories is being able to detect whether it's a TV, sofa, chair, table, and so forth, which all these were previous either object or furniture categories. And so here are some examples of the type of predictions our framework makes. So here is an example of the scene. This is how the ground truth labels look like. These are how our predictions look like using only the enriched set of features which we compute. So we, in addition to the geometry, we also compute some texture features and some more sophisticated color features. But now, using the per object category grouping rules, the conditional random field framework really does much more work and very nicely refines the segmentation in order to generate the proper results. So here are some more examples. So I would like to conclude by hopefully giving you some feeling about that there is actually a big promise in developing computationally efficient approaches to semantic segmentation. And we can effectively use multiple sensing modalities, and sort of setting up the problem in 3D enables us also to nicely integrate these techniques with the SLAM methodologies, and how we can use the robotic tasks to efficiently sort of construct the semantic hierarchy and refine our representations based on the tasks, and then also build them furthermore incrementally by always learning how these different objects appear with respect to background. Thank you very much.
Hi, my name is Umar and I am a PhD student at the University of Western Australia. My research work is related to the task of object segmentation in highly complex human living environments for robot manipulation. Our overall objective is to design a vision-based robotic system, a perceptual system which can be integrated into existing robotic applications for executing high-level tasks such as object grasping. In this particular paper, we presented a heuristic-based approach to segment unknown stacked objects in highly complex scenes. This is intrinsically a challenging problem, especially when the scene contains a large variety of objects stacked in unpredictable orientations and layouts, and no prior information about the size, shape, or physical appearance of the objects is available. This difficulty is compounded with the additional challenges of real-world environments, such as variable lighting conditions, variable viewpoints, shadows, illumination artifacts, and most importantly, noisy observations from low-cost sensors such as Microsoft Kinect. Our approach can be split into two main stages. In the first stage, we generate an initial segmentation of the scene into mid-level regions. Specifically, the algorithm starts from a seeding step where initial region centers are seeded on an unlabeled point cloud. Next, we grow regions from these seed centers by collecting points from the local neighborhoods, which are similar in terms of their surface normal orientations. In the next stage, we merge perceptually similar regions to form high-level object hypotheses, which highly likely correspond to distinct objects in the scene. Here, our merging criteria is motivated by the fact that unique objects appear in the scene as protrusions from their sporting surfaces. Therefore, surfaces which are either coplanar or convex, they belong to the same distinct object and should be merged together. Here we show some videos of our experiments using live video streams from the Microsoft Kinect. We show videos for our object segmentation algorithms, where in the top video, the algorithm is working in an automatic mode so that it automatically segments all objects which are within the field of view of the camera. In the bottom video, our algorithm is working in an interactive mode where it provides the user the ability to segment any particular object. This can be advantageous in a task where it is required to grasp a particular object from a heap of piled objects. We also performed a grasping experiment where the robot is directed to put away all the objects placed in front of it, just like a table cleanup experiment. For further results and technical details, I look forward to seeing you all in the interactive sessions. Thank you.
Good afternoon, my name is Federico Tombari. I come from the University of Bologna. This talk is about the detection of pod-like structures in urban environments. We're witnessing a huge increase in the amount of 3D data that is available, and it is being acquired from laser scanners on top of roaming vehicles. This data is still mostly processed via manual annotation, so tools that can automatize this process are of high interest in research. In particular, we're looking for pole-like structures, so we want to build an algorithm that outputs something like that, so 3D bounding boxes of pole-like structure, including road signs, lampposts, utility poles, and traffic lights. This is extremely important for applications such as road monitoring and maintenance, and also autonomous navigation. Unfortunately, these structures are particularly challenging. Indeed, there's a lot of clutter and occlusion in this data. As well, they exhibit huge and strong shape variations among the same category. Also, they are made of a very thin size and low density, just a few tens of points per object, and it's very hard to discriminate between pole-like structures and tree trunks. In a nutshell, the pipeline that we propose, apart from an initial pre-processing stage where we basically detect and throw away the dominant planes in the scene, it's based on a two-stage approach. On the first stage, we do a point-wise classification, so we extract a feature that we propose as a contribution of this work, and it's aimed at detecting the poleness of a local neighborhood of points. Afterwards, we apply a macro-random field model in order to enforce spatial smoothness among the labels that have been classified, so that we get less false positives as well as clusters. These clusters are then used in the second stage, where we apply another classifying stage, but on a cluster rather than on a point level. In this case, the feature that we apply exploits context. And this is particularly useful to distinguish between pole-like structures and tree trunks. We have tested our approach on two data sets. One is the public benchmark CMU Auckland. The other one is a data set that we acquired ourselves. And on one of the tests that we proposed in our paper, on a cloud of 33 million points, we obtained 75% of the poles correctly recognized against less than 20% false positives. So if you want to know more details, and if you find this work more appealing than the concurrent open bar at the farewell session, please join me for more details at the interactive session. Thank you.
Good afternoon. My name is Dominic Honecker, and I'm going to present our work on computer vision hardware based on a combination of an FPGA and a mobile CPU. This work was done at ETH Zurich. So today's smartphones are kind of the ideal platform for mobile robotics applications, as they are small in size, lightweight, and they contain a variety of different sensors, as camera sensors, inertial measurement units, or GPS sensors. However, the computational power of these devices is still limited, so you can record and playback videos at high frame rates and resolution, but you cannot fully process them. So you cannot calculate a dense flow field or a dense disparity map at this high frame rate and resolution. So let's take a look at the architecture of such a mobile system with a camera. The camera is connected to the mobile CPU. There is a frame grabber involved that transfers image data to the system memory for further processing. We now propose to add an additional layer between the camera and this mobile CPU, an FPGA. This is a field programmable gate array. Roughly speaking, a computer chip, you can design the internal configuration the way you want. The FPGA is kind of a hidden layer, as it acts towards the mobile CPU as a regular camera and towards the camera as a regular mobile CPU, and is therefore fully compatible with the existing architecture. Using now such an FPGA allows you to easily build up a multi-camera setup with 2 or 3, 4, 5, or as many cameras as you want. And more importantly, you can offload computational intense computer vision tasks from the mobile CPU to the FPGA. We built a prototype device with an FPGA and a mobile CPU for dual camera support. And even though there is an additional chip now, the FPGA, the power consumption of the complete system, camera, FPGA, mobile CPU, is still quite low. As an example computer vision application, we implemented a well-known semi-global matching stereo algorithm, including subsequent tasks as lens distortion correction and rectification. It runs at frame rates of the image sensors, and the latency is also quite low. You can see in the video the output with the disparity map on the left and the raw image data on the right. So I'm happy to welcome you at my stand during the interactive session, and as the interactive session is in conjunction with the farewell party, we may also can have a beer together. Thank you.
Hello everyone, I'm Lars Peterson and I'm with NICTA, National ICT Australia. I'll present the paper Multi-View Terrain Classification using Panoramic Imagery and LiDAR. I present this on behalf of Sarah Namin and Mohammed Al-Jafi, as they unfortunately couldn't come here and present it themselves. So the problem we're looking at here is to robustly classify terrain given a 3D point cloud and a set of panoramic images. And this point cloud data comes off of Velodyne 64 that I'm sure many of you are familiar with. The kind of output you see from them is what it looks like in this picture here. And the panoramic images, they come from a Ladybug 3 camera, as you can see here. So one of the problems that you face in outdoor environments is that often regions appear very dark or they are saturated by the sun. And this means that in those regions, the information is essentially destroyed, which means that you can't accurately predict which label that region should have. Another problem that often occurs in the real-world system is that the point cloud and the panoramic image become slightly misaligned with each other. And this is because of a time-varying pose-estimation error of this surveying platform. The kind of objects that are the most affected by this are thin, narrow objects like wires and poles. So the idea here is quite obvious. Well, we use multiple views of the same 3D point and try to combine them in a smart way. So obviously this relies on the underlying assumption that on average most regions are good most of the time, and most of the time the misalignment problem isn't too severe, and the task here is to reject outliers. So the system that we have constructed looks as follows. For each 3D point we find a set of nearby 2D regions in the imagery, and for each one of these 2D sets we find the most representative 2D feature through a consensus process, and this consensus process is described further in the paper, and I can tell you more about it in the interactive session. The representative 2D feature and the corresponding 3D feature is then fed to a fuzzy support vector machine that gives unary potentials, and these unary potentials are then fed to a conditional random field that predicts the final label. So looking at the results, we see that obviously the multi-view approach is considerably better than the single view approach. But if we dig down a little bit into the statistics there and we look at the sine pole and the power pole classes, we see that they do particularly well as they are narrow classes, which is what we designed for. Thank you for listening.
Hello everyone. So I'm presenting this paper on behalf of the authors who could not be here today, and they gave me a script, so I'm just going to read through the script. So we present fast and efficient methods for visual loop closure detection in appearance-based navigation. The widely used technique based on the bag of words image representation has shown some limitations, especially with the aliasing problem. So in this work, however, an appearance-based approach for loop closure detection using local invariant and color features is proposed. The first technique uses Bayesian decision theory for loop closure detection based on Gaussian mixture models. And the second technique is based on a combination of GMMs with KD trees. So given a query image for loop closure detection, we first extract features, and if not enough motion is detected, a GMM will be fitted to the extracted descriptors. The output of these modules are GMM dictionaries, which will be used as inputs to the Bayesian loop closure detection module. And this is repeated until enough motion is detected. Once we have enough motion, the Bayesian loop closure detection module is triggered using the GMM dictionaries as input. The output of this module is a candidate frame for loop closure. If the epipolar geometry check is successful for this candidate frame, the loop closure is accepted. Otherwise, it will be rejected, and we move on to the next keyframe. The second technique is based on a combination of GMM with KD trees. Given a query image, a GMM will be fitted to the extracted descriptors. And again, if not enough motion has occurred, a KD tree is constructed over the k-means. This process is repeated until we have enough motion. In which case, a nearest neighbor search is performed in the KD tree after assessing the quality of these matches. If no frame passes this threshold, loop closures will not be declared. Otherwise, there are two options. The first one is to use the technique described before, and the second one is to use the full KD tree data structure. If epipolar geometry is successful, the loop closure is accepted. Otherwise, it will be rejected. And here we present some results in an outdoor setting. The graph shows the number of assignments of all previously seen frames for two descriptor spaces, that is SIFT and color. This is another example from some outdoor environment. The table shows precision, recall, and accuracy. And this is an example of loop closure detection using the combination of GMMs with KD trees data structure. Thank you.
Good afternoon, everybody. Thank you all for being here. My name is Henry Carrilla. I'm from the University of Zaragoza. And today I'm going to talk about the paper entitled Place Categorization Using Sparse and Redundant Representation that I have done jointly with my colleague Yasir Latif, Professor Jose Neira, and Professor Jose Angel Castellanos. So before talking about the problem we are facing here, let me start with a definition of what we consider a place. So for us, a place is a confined location with an indoor environment that in which activities with a common name are carried out. And in particular, we consider that a place can be defined by the relation of the object within the environment. So the problem of place categorization is the one of assigning a semantic label to the robot's current location, giving a snapshot of the environment. So we are assuming that the only available information to the robot is of the visual kind. And also we assume that the robot has seen a similar environment before, that is a training set available with semantic labels on it. So why do we care about this problem? Well, being able to categorize a place allows a robot to solve easily high-level tasks such as clean John's office or go to the kitchen and bring me water. So in this paper, we use a sparse and redundant representation. As the name implies, the idea is to model the problem redundantly, and given an observation, we look for the sparsest subset of this model that explains the current observation. This framework has been used widely in the computer vision community, and if we consider a linear system, the main question is, how does A explain B? And in this case, B is our current observation, and A is the so-called dictionary that includes the previous information that we have about our problem. So in this case, because the assumption of redundancy, we have more columns than rows, so that our system is undetermined. That means we have no solution or infinitely many solutions. And in the later case, we would like to assess, to look for the solution that is more meaningful for our case, that is the sparsest one. So posing the place categorization problem in this framework, we could use B, the current observation, as a descriptor of the scene. And A is going to be a stacked observation from our training set. In order to find out the sparsest solution, or the simplest one, that explains our current observation, we have to solve this optimization problem using the L0 norm. The good thing about this is that it's going to give us the optimal solution, that is the sparsest one, but this problem is NP-hard. So if we realize this optimization problem using the L1 norm, we're going to have a solution that is sparse enough, but is tractable. So please join me in the upcoming interactive session to explain you further about this approach and to show you some experiments. Thank you.
So I'm presenting this paper on behalf of the author, who is not here. So the title is Real-Time Global Localization of Intelligent Road Vehicles in Lane Level via Lane Marking Detection and Shape Registration. The system contains 3 modules. The first module is lane marking detection, providing local localization of the vehicle. The second module is GPS localization, providing a coarse global localization and a road shape prior. The third module is cross-validation between lane marking results and the road shape prior. By checking the geometry consistency, the module validates the lane marking detection and improves the overall performance of the localization system. The authors adopt a 3-lane model for assigning the semantic attribute for each detected lane marking. The lane marking system provides a stable and robust multi-lane marking detection with a local localization accuracy of centimeter level. Lane marking detection is performed by integrating vision-based detection of lane markings and camera pose with IMU. An high-accuracy lane boundary map is also built offline as a digital map made by a set of points. Each point contains the global position of the leftmost boundary and the rightmost boundary of the road. All these positions are collected by an intelligent vehicle equipped with GPS and are corrected by a semi-automated method. This ensures high accuracy up to centimeter level in the map. A sequence of these points constitutes the description of the road shape. However, when the vehicle is driving autonomously, the GPS position measurements may contain shifts from the actual position due to signal masking. Thus, the authors extract a possible road shape prior from the map corresponding to the actual image seen from the camera, and the authors show that by formulating the positioning system in a relative way, they can estimate the vehicle localization in real time. The validation scheme integrates the vision-based lane detection with shape registration. Geometry consistency is tested by applying an ICP-based shape registration algorithm. The algorithm aims at finding the transformation that best aligns the detected lane marking from the vision system with GPS road shape prior. The Euclidean distance between the lane markings and the GPS road shape prior indicates if the lane marking is geometry consistent with road shape prior or not. If the geometry consistency is satisfied, then the transformation estimation in the previous step is used to correct the GPS drift. The system is implemented in a prototype intelligent vehicle and has been tested extensively under different challenging environments. And more results will be provided in a video in the interactive section. So if you have questions, please ask to the authors. Thank you.
Hello, my name is Jimita. Instead of the first order Chang-Wao, I would like to explain on-road vehicle detection through part of model running and probabilistic inference. Motivation of the objective is to achieve robust on-road vehicle detection. On-road vehicle detection have various appearance with different viewpoint, just the first row pictures. And also, these are easily occluded by other objects, the infrastructure, cars, or the pedestrians, like that. So, in order to overcome this kind of detecting difficulties, we propose the probabilistic framework for on-road vehicle detection. This is basically composed of 2 parts, offline learning and online processing. And offline learning basically model running, and online processing is just the testing and output, vehicle position, and pose. And the offline learning, we add the 2 features, part run the geometric model learning and probabilistic viewpoint map generation into the original deformer part model. This is the part-based vehicle model. This is just the each vehicle part distribution from vehicle center. And the probabilistic viewpoint map is just to correspond to the, road area specific probability for each viewpoint. This is our result. So the occlusive part is very sophisticatedly detected. Thank you very much.
Okay. I'll be talking about a real-time method. I'll be talking about a real-time method for depth-enhanced monocular odometry. This is a virodometry method, and it's classified as RGBD virodometry because it uses monocular imagery plus additionally provided depth information. It supports 3 sensor configurations now. It supports RGBD cameras such as Kinect and Action Pro. It supports camera plus custom-made 3D LiDAR, and it supports the KT Vision benchmark setup. For the KT Vision datasets, we use the Velanine laser to get the depth information, and we use the images from a single camera out of the stereo pairs. This method is ranked number 3 among the overall evaluated methods, but it's not a fair comparison because all the other methods use stereo vision, and we use Velanine to get accurate depth, which is way more accurate than stereo system. But we want to use this to deliver a message to the research community that is, why not using a camera and laser together for odometry estimation? We know this is doable, and we know cameras are so good at acquiring 2D information. Lasers can get accurate depth, but we just don't see many people pursuing this option. Now, in fact, this method is also partially used in the number 1 ranked method. Now, different from the existing RGBD virodometry methods, in this one, we try to maximally utilize the features with and without depth. It combines 3 types of features. First, it registers a depth map with depth from RGBD cameras or LiDARs using estimated motion of the virodometry as these white points. Then it tries to associate depth from the depth map to the tracked viro features as these green points. If that option is not available, it tries structural motion to retrieve the depth as these blue points. And as the last option, it can still use the features without depth at all as the red points. A feature with depth can derive 2 lines of equation, and the feature without depth can derive 1 line of equation. The motion estimation is to solve a nonlinear optimization problem, combining equations from features with and without depth. This method also has a boundary adjustment step that uses ISAM to refine the motion estimates. This step processes sequences of images in batch optimization, and the virodometry output is a combination of the boundary adjustment and the frame-to-frame motion estimation. Now, in the end, let me encourage you to download and try it out on your computer. The code and datasets are publicly available. The code is written in C++, and it uses ROS. Thank you.
Hi, I'm Thomas Koleczka, and I'll be presenting MIVO, a multi-environment stereo visual odometry framework that I've worked on with Louis Puig and Kostas Danilidis at the University of Pennsylvania. As robots and humans equipped with stereo cameras advance into both indoor and outdoor environments, it is important to have robust odometry estimates in any type of environment to be able to track the movement. Notice that indoor environments feature mostly very stable line features, whereas outdoor environments are crowded with point features that can be tracked. Most existing approaches focus on either indoor or outdoor environments and want to deploy the robot in these environments. However, these approaches often lead to visual odometries that are only stable in one environment, But we propose in this work the combination of both point and line features to result in a more stable stereo-visual odometry in both types of environments. Disparity computation for line features is more challenging than it is for points, as it is not possible to do descriptor extraction and matching in real time for line features. Hence, we propose a new real-time line stereo matching algorithm. First, we detect the lines in the left image. Then we extract a number of sample points for each line. And then we use a modified block matching approach, which searches in the search window, just like the classic block matching approach, but it only considers pixels that have a similar gradient magnitude and orientation as the sample point in the left image. Finally, we compute the subpixel disparity at the line segment's endpoints by robustly fitting a line to the sample points in the right image. This allows us to be more robust to occlusions and false matches in the right image. We use maximum clique as inlier selection for both point and line features based on 2D and 3D consistencies. Using both the 3D point and line detections from the previous frame, we then estimate the incremental motion by projecting the 3D features from the previous frame into the current frame and minimizing a nonlinear least squares problem. Finally, we evaluate the method in both outdoor and indoor environments and compare to other approaches such as Liviso. If you'd like to know more details, please visit us at the interactive session and have a beer with us. Thank you.
Good evening. My name is Johnny Park. The title of our paper is Place Recognition and Self-Localization in Interior Hallways by Indoor Mobile Robots, a signature-based cascaded filtering framework. This work is by Halil Ahmad Yusuf, myself, and Avi Kak at Robot Vision Lab of Purdue University. So we present a robot self-localization method based on a cascade of filters that increasingly refine robots' location in a hallway system. So one of the goals is to use any existing map to build a model representation of that indoor environment, then to use that model later on for the purpose of place recognition and robot self-localization when the robot is an autonomous run. Place recognition in indoor environments is challenging mainly due to varying illumination conditions and the fact that there are visually similar objects repeatedly placed in the hallways, and finally the fact that some places have very few or no features to extract. So we propose a signature-based cascaded filtering framework to address this challenging problem. A central question in this approach is what signature-based filters to use for each stage of the cascade. For early stage filters, we would like them to be very fast, viewpoint invariant, and moderate locale uniqueness. On the other hand, for downstream filters, we would like them to be viewpoint variant with high locale uniqueness because we want to precisely localize the robot position and orientation. So in this paper, we present a novel criteria for selecting the best signatures for early stage filtering as well as downstream filters. In order to create a cascade filter, we need a set of features. For this purpose, we use 3D junction features called 3D judoka, which we proposed in earlier work. The 3D judoka features possess several characteristics that are important for indoor hallway place recognition. Using 3D judoka features, we then extract what we call locale signatures. We use the notion of a signature to be a summarizer of the features that can be used to characterize a locale in the hallways, and also to be used in each stage of the cascade. The proposed framework was tested in a large indoor hallway system with a total linear length over 1.5 kilometers. This data was collected in the hallways of 3 buildings at Purdue University that possess several challenging scenes, as I alluded earlier. Our proposed signature-based cascade filtering framework results in significantly faster place recognition with comparable accuracy compared to a traditional RANSIC approach. Thank you.
Hello everyone, my name is Siddharth Jain and I'm a PhD student at Argal Lab at Northwestern University. And I am presenting the paper here, Automated Perception of Safe Docking Locations. Powered wheelchairs provide mobility solutions for users who are unable to operate a manual wheelchair. But there are certain tasks with the powered wheelchairs which can be difficult for the users. Approximately 57 million people had a disability in 2010 in the United States, and almost 40% of them were not able to do activities of daily living. Smart wheelchair research often provides solutions to assist people in performing activities of daily living. Examples of such behaviors are obstacle avoidance, doorway traversal, docking, or wall following. Out of these, docking behavior is minimally addressed. What do I mean by docking behavior here is maneuvering the wheelchair to a free space underneath a table or a desk such that the person using the wheelchair is able to interact with the surface. Finding docking locations is very important in context of assistive wheelchairs as well as for autonomous mobile robots. However, perception of such docking locations is a complex vision problem. First of all, we need to come up with the safe locations underneath the candidate structure, but then also we need the alignment information to perform the docking. And also, in order to provide the general solution, the algorithm should be free from customization or free from usage of fiducial or landmarks. Our algorithm handles all of these behaviors. Here is the overview of our work. We have this smart wheelchair platform in our lab, and it is equipped with a Kinect sensor, which is mounted about 130 centimeters above the ground floor. The input to our algorithm is a point cloud of the scene, and we are just using the depth data. Most of the docking structures are either circular or rectangular, and our algorithm handles both. Furthermore, we also have a safety determination using the ADA specifications. Firstly, we classify the candidate docking structure either as a rectangular or circular by using half circle detection over the point cloud boundary. Then we have two approaches which we have combined into a single algorithm. Our first approach is an open search, which is a sequential search around the candidate structure which identifies safe segments. The second approach is based on a dinner table or a restaurant setting in which objects such as cups or mugs are placed over the table. Our insight is such that such objects mark desired docking locations. Here is the illustration of the two approaches on the desk structure. We have verified our algorithm on a variety of docking structures from varied viewpoints. And if you're interested to listen more, please come to my interactive session. Thank you.
Hello, my name is Krzysztof Walas. I'm from Poznań University of Technology, and together with my colleague Michał Nowicki, we performed some experiments on terrain classification using laser rangefinder. So we posed the problem as follows. So we want to have a terrain classification for a mobile robot, which will enable adaptation to changing traction conditions. And we're going to use laser rangefinder and obtain the data from distance and intensity values. We had 12 terrain types, such as rubber, wooden boards, several types of rocks, pebbles, artificial grass, concrete floor, ceramics, carpets, and sand. And we registered the data using two Hokuyo scanners. We also had 3 heights above the ground when we are moving to the ground. We performed our experiments in the presence of artificial light and also in the presence of the daylight. And we also registered distance and intensity values, taking into account automatic gain control. So we aligned those scans to obtain the patches, and we tiled the whole terrain into patches 10 by 10 centimeters. Then we proposed several features. So we tried textons with k-means on the histograms of those textons. Then we also used statistical approach, and we also used 2D fast Fourier transform with using those masks which are presented. And then we fed all those data to SVM classifier, and we also performed some combination rules on top of those classifiers. And the results are as follows. So we had one of the largest terrain set for the research which was done in, for our as our colleagues did it. And we obtained the precision of the combination of 2D fast Fourier transform with statistical approach at the level of 98%. It is, of course, test data set. And the speed of this approach is that, for example, if we take a 2 square meter map, so it is 400 patches, we're going to have 87.5 milliseconds for one such a scan, for one such a whole scene. To compare also our results also were using other modalities, so they were using multispectral images and vision and vibration. We only were using intensity data from the scanner, and the results are as follow. So if you would like to know more details about our approach, please come to interactive session. Thank you very much.
Okay, hello everyone. My name is Yuan Yixuan, a third-year PhD student in the Chinese University of Hong Kong. And today, my topic is a novel feature for polyp detection in wireless capsule endoscope images. This is the work I did with my supervisor, Max Qinghu Meng. Wireless capsule endoscope was introduced in 2000. It is a revolutionary device that provides direct visualization of your gastrointestinal tract. However, the major disadvantage of this technology is that it will create 50,000 images for one patient. Moreover, polyps is one of the most common diseases in GI tract. It affects many people around the world. So our aim is to detect the polyps automatically in the WCE. This is our proposed method. First, we utilize the Gabor filter on the original images to obtain information in different scales and orientations. Then, mono LBP descriptors is applied on the corresponding Gabor filter responses. The mono LBP is an extension of LBP, and it adds local phase information to the traditional ones. The local phase information corresponding to the local measure of the local structures. And then it is environment to the illumination and noise. So after that, we combine these mono LBP descriptors together and apply linear discriminant analysis on the features to get the final features here. And we know that WCE are the color informations, so we investigate the proposed feature in different color spaces like RGB, HSV, LAB, and then conduct experiment using 413.6 normal images and 413.6 abnormal images. This is our result here, and this shows classification performance for different color channels. We can find that our best performance can be obtained in the L component in the LAB color spaces. Our result is very inspiring, showing that 91.43%. Moreover, we compare our method with 4 traditional measures here. We found that these features are LBP, BGP, MLBP, and Li Baopu method. Li Baopu focus on the same topic as ourselves, but we found that our method shows better performance than all these methods here. So thank you very much. I'm looking forward to meet with you in the interactive part. Thank you.
Hi, my name is Aitor Aldoma, and I'm going to talk today. I'm from the University of Vienna, and I'm going to talk today about the acquisition of ground truth data for object instant recognition datasets. This work was inspired by the limitations that techniques that are using fiducial patterns have. In particular, they impose constraints on the scene layout, the number of objects that can be annotated, as well as on the position and orientation of the objects in the scene. As a result, the data sets that are collected with this kind of techniques do not fully capture the challenges posed by object recognition in real-world scenarios. Instead, in this work, what we do is we suppose that we can move around a static environment with an RGBD camera and then formulate the annotation of ground truth data as a multi-view object recognition problem. And we argue that the results that we obtain in this multi-view setting are very close to the ground truth of the actual data. We use this algorithm in order to annotate to data sets with more than 3,500 object instances, and the results were quite well. In particular, for the Willow data set, we were able to annotate 99% of the object instances, and for the more challenging TUVIN data set, we were able to annotate 93% of the objects. So how does this method work in about 1 minute? Basically, we start by recognizing and detecting the pose of objects in each of the input frames. In particular, here we're using the single view method that we proposed last year at ICRA. Then we create a so-called multi-view graph with as many nodes as input frames. And then we create an edge between two nodes whenever we have detected the same object in 2 frames, or both frames were, or it was able to register them by means of visual features. Each edge contains a transformation that registers 1 frame to the other, as well as a weight indicating the quality of the pairwise registration. Then we can extract the minimum spanning tree of this graph in order to align all frames into a world coordinate system, as well as to create a 3D reconstruction of the scene. In the next stage, what we do is we project all the single view results into this world coordinate system, and then through a multi-view verification stage, we extract a subset of them that best represent the scene that has been reconstructed. Finally, we just back project this verified hypothesis into the original frames and consider these back projections as the ground truth data of the original frames. Thank you very much for listening, and visit us at the upcoming interactive session. Thank you.
Good afternoon. My name is Yoon-Seok Choi. I'm a PhD course student in Sangkyungan University. Today, I briefly introduce about recognition of inside pipeline geometry by using PSD sensor for autonomous navigation. Pipelines are the major infrastructure for transporting gas, oil, and other fluids. They are required regular inspection and maintenance. As shown in this figure, to reduce time and cost of inspection process, many researchers have developed the inspection system by using robot. However, currently commercialized in-pipe robot is manually controlled by operator. For autonomous navigation, the robot is able to recognize the inside pipeline geometry. For this work, we have to classify the element type, such as straight, elbow, branch, and miter, and to figure out the opening direction of pipe element for steering. In our lab, we had developed the vision process to detect pipe element type and opening direction. However, this method is so sensitive that is weapon noise, and we cannot distinguish between T-branch and miter. To solve this problem, we used the PSD sensor to recognize the inside pipeline geometry. As shown in this figure, we have developed the sensor suite, attachment 9 PSD sensor, and the driving module named the MR Inspector 6 is used for driving. By using PSD sensor, we can get the distance information between sensor suite and inside of pipeline. By using this information and simple calculation, we can detect the pipe element type and opening direction. This video is experiment result in pipe miter type 2 pipe. As shown in this video, we can detect pipe element type and opening direction by using PSD sensor and simple calculation, and it can possible to detect miter type. As a related paper, the paper about the driving module of our project is also offsetted in this conference. If you have interesting or question, please come to my interactive session. We can discuss this the detail of this subject in a coming interactive session. Thank you for your attention.
Okay, hi everyone. My name is Marian Himsted, and I'm from the University of Lübeck in Germany, and I'm presenting our approach on place recognition using 2D LiDAR scans based on geometrical landmark relations. And the difficult part when working with 2D LiDAR compared to, for example, images is that you only have a very, very small subset captured from the environment. So when you want to recognize places and associate it with places we have already seen before, we need to detect some kind of stable features that serve as our landmarks. And what the state-of-the-art actually does is they look at these landmarks and capture the surroundings of those landmarks and get descriptors for them in order to associate it with others. What we're doing here is different from that. We are looking at the geometrical relations of the landmarks, so that is the distances and bearings, and looking at it in detail, like on the left up here, we see one example. Then we're getting the distance and the bearing for that one, and we quantize it to a 2D Gaussian. And if you apply that to all the relations you have in that scan, we get these nice glare signatures, and they are very, very robust in terms of changing viewpoints and can be used efficiently to search at very, very large scale. And the key idea that we proposed here is not only relying on the appearance of descriptors, but also on how landmarks are related to each other. And actually encoding that into a representation turned out to work very well. And we evaluated that on publicly available datasets for indoor and outdoor settings. And you can see the state-of-the-art flirt is much worse than our proposed approach. And also on the quite difficult Victoria Park dataset, we are achieving very good results. And we're not only better than the existing approaches, we're also faster. So I'm looking forward to see you at the interactive presentation. I'm happy to give you more details about our approach. Thanks.
Good afternoon, everyone. My name is Haider Ali, and I'm working at Institute of Robotics and Mechatronics, a division of German Aerospace Center. And I'm going to talk about the evaluation of feature selection and model training strategies for object category recognition. So as we all know that a usual problem in object category recognition is that the generalization approach works pretty well on the data it was captured under similar circumstances as the training data set, but typically we cannot generalize it to the data acquired differently when the domain change occur. So the goal of this work is like we are going to evaluate RGBD feature selections, strategies, and the feature extractors to identify which remains less effective in the domain change problem. So the focus is purely on categorization when the testing objects are completely new to the classifier. So as a part of this work, we investigate PFH, VFH, and ESF point cloud library-based features, and we wanted to discover that which part of long histograms are more descriptive and informative for the category recognition in case of domain adaptation. So we performed these experiments on RGBD and DLR dataset. And as a feature selection for categorization, we can see like all dimensions and the feature chosen by MaxRel and MRMR, so using all three types of features. So we have compared MRMR and MaxRel on DLR dataset using the concatenation of all three features. So we can see on the upper graph that the best 50 dimensions of MaxRel already give good results. So similar to the down bar, we can see like we have run 10 runs for the all type of features and 5 runs for MRMR and MaxRel. So on the left side, we can see like 33% data has been used and 66% data for for the domain on which the training has been done. And on the left side, we can see that by adding a fraction of the target domain, we can already achieve a significant improvement in the results. So to make sure that no objects for training are reused for testing. So the classifiers were trained on database, performed poorly on a new data set, and randomized cross-validation is not a good indication in our science. We found that the Lee-1 bootstrapping test on RGBD was too optimistic. So improvement is not due to the size of training data set, but average accuracy does not change much as the object changes, and we found that VFH part of the PFH were more informative. So if you're interested, please join me in the interactive session for further questions. Thank you.
Hi, good morning, good afternoon, everybody. My name is Karin Ramirez. I'm doing a PhD under the supervision of Professor Gordon Cheng and Professor Michael Bitz at the Technical University of Munich. And today I will discuss about the semantic representation and recognition of human activities from observation using semantic reasoning. So our main motivation is to enable robots, as you see in this video, with learning capabilities. That means that the robot needs to segment and at the same time recognize what the human is doing. Additionally, the robot needs to remember and use the previous experiences when new activities and new scenarios are shown to the robot. So segmenting and recognizing human activities from a continuous video stream is a very challenging task. For example, if we observe the activities produced by a similar activity, we can see on the left side that these trajectories are completely with different behaviors. Then we are proposing that these trajectories, we have on top of this trajectory level a semantic reasoning engine, and the combination of the trajectory level and the semantic reasoning engine, then we can cluster the activities in a meaningful way. In this case, our framework has been validated using the perception, a very naive perception system, which in this case is a color base. And from this color base, we have atomic motions of the hand, like move, not move, and tool use, and only two object properties, object acted on and object in hand. This information is used in our representation, in our semantic representation, and as a consequence, then we can recognize more complex human activities such as reaching, taking, cutting, etc. The accuracy of recognition of this complex activity is quite high, which is 80% accuracy. And the most interesting thing is that we have transferred all these models into the robotic system. In this case, we are using the ICAP as a research platform. And the interesting part is that the video that the robot is now observing has never been seen before. That means that the robot is using the previous experiences from scenario 1 so that he can recognize a completely new scenario. Additionally, the robot is able to detect when a new activity has been recognized, and via active learning, he is able to learn on-demand new activities. If you are interested on the methods that we have used to transfer these models into robotics, please come to the interactive session, and I will be very happy to answer all your questions. Thank you very much.
My name is Yoshitaka Hara, a PhD student at the University of Tsukuba, Japan. I will talk about detection of liquids in cups based on the reflection of light with the depth camera using triangulation. Our objective is liquid detection. We propose a method to detect liquids in cups with the depth camera using triangulation like ASUS action sensor. The upper right figure shows the side view for point cloud of the empty cup. A measured point cloud of the cup bottom was in contact with the desk plane. The lower left shows the case of opaque milk tea. Point cloud that seems to be the liquid surface was measured. The lower right shows the case of transparent water. Point cloud of the cup bottom was raised from the desk plane. This point cloud is not the liquid surface. In summary, in the case of opaque liquid, the liquid surface was measured. On the other hand, in the case of transparent liquid, raised cup bottom is measured. So, why measured points of the cup bottom were raised for transparent liquid? It is because the projected light of the action sensor is reflected at the liquid surface. This figure shows a bird's eye view. The projected beam is reflected at the liquid surface, and the received beam is also reflected. Therefore, the apparent measured point M is raised from the cup bottom. The theory of raised points is based on Snell's law that represents the reflection of light. We propose a method to detect the presence of liquids in cups based on this theory. This figure shows the processing pipeline of our method. Cup recognition is performed with the least squares method and ICP matching. Liquid detection is performed with the theory of raised measured points. Our method is capable of liquid detection in cups for various degrees of transparency. This table shows experimental results. There was only one false positive in the case of the empty cup. The recognition rate of the liquid detection was 99%. The contribution of our research is success of liquid detection for various apparent or transparent liquids, which include clear water. Thank you for your attention.
Thank you.